Hola, ¿te molesta con esto otra vez? Sí, acá en la polera mejor, pero no. Apretando tanto y está ahí.
Vale. ¿Qué es eso?
Para calefacción.
Ah, bueno.
Los secretos.
Exacto.
¿No es la proyectar
No,
nada,
no,
¿cierto? ¿Solo pizarra?
Solo pizarra, gracias.
Me voy entonces.
Vale.
Gracias.
Should we start?
Sure, thank you. Please.
Okay, guys. Well, welcome back. So we restart the afternoon with the second lecture of the lecture series of Sebastian Herrero on Hecke orbits and equidistribution.
Thank you very much. So we will continue with what we were doing yesterday. So I just wanted to quickly remind you about this important definition, because this is what is called the Hecke orbit of a point for each n. So here n is a positive integer. So yesterday we defined these objects, these Hecke orbits, and at the end we said that we were interested in the kind of properties of these orbits. For example, knowing if this collection of points, if you want, because this is it's almost like the collection of all possible quotients of E by a subgroup of order n. But we define it in a way that we take into account multiplicities, so that's why we use the language of divisors. And the main questions were about the distribution properties of these points in the moduli space of elliptic curves, and also asking about if these points become dense or not in this space with respect to certain topology that we have to take into account. Today will be more about the second part of the title, so equidistribution in general, and then at the end I hope to come back and bring these two things together in at least one case where the base field is the complex numbers. Okay, this is the important definition, and now, where am I? Okay. So today I want to talk about, let's say this is section 3, I guess, uniform distribution or equidistribution. So also I should remind you that the number of points in these divisors, the degree of this divisor is sigma 1 of n, the sum of divisors of n, and this number grows. So every time you have a nice space and then you have a collection of points, a collection of, let's say, a sequence of sets of points whose cardinality is growing, you can ask about the distribution properties of your sequence. And it's very nice when people manage to prove some uniform distribution results. So let me give you one reference on this topic. There's this book, Equidistribution in Number Theory. Where you have several articles that discuss different equidistribution problems in different settings in number theory. Actually, one of the papers that is included in this book is about the uniform distribution of CM points, and I will come back to this later. This is by editors Granville and Rudnick. Okay, and as I said yesterday, in order to give a formal definition, give a formal idea of what uniform distribution is, we need some measure theory. So let me do some general definitions. So somehow we will forget for a moment about elliptic curves and moduli spaces. So let me give you some definitions. So let's start with a metric space X, and then we denote by P of X. This will be the set of all probability measures which are defined on the Borel subsets of X. So this is the set of all Borel probability measures on this space X. And uniform distribution statements are presented in terms of convergence of measures. That's why we have to introduce this notion. So let me continue here. So a sequence of measures, let's say mu n, we will say that it converges. There's different notions of convergence of measures. I will just use one of these, which is the weak convergence. So converges weakly to another probability measure in the same space if the following happens: for all functions from x to r, let's say, continuous and bounded, we have that the integral of f with respect to this sequence of measures over x converges to the integral of f with respect to the limits measure. So this is one notion of convergence that we will use in order to define equidistribution. So now let's consider a sequence of sets. So sequence of subsets xn of x, finite subsets. And for each one of these, we will construct a natural probability measure, which is just the sum of the Dirac measures on each point of this set. So define, and I will write delta for the Dirac measure, but this is kind of an average over the set xn. Of course, here I need xn to be non-empty. This will be 1 over the number of points in my set, and then I just put a Dirac measure on each point of the set. And this is just the measure that gives value 1 at each set that contains x, and it gives 0 if the set does not contain this point x. Okay, so now I can give you the definition of uniform distribution with respect to a limit measure. So we say that xn is uniformly distributed with respect to some measure mu, as here it will be the limit measure, if the corresponding sequence of Dirac measures converges to mu. So if delta bar xn converges to mu weakly. Okay. So, yep.
When you wrote finite, it means the measure on x is finite, right?
I mean that each set is finite set. Finite sets, these guys, the xn's. So the x will be in general a big space, an infinite set, but each xn is finite, so this is a finite sum. Yeah. Okay. I will try not to write here the lower part of the whiteboard. Okay, so this general definition. So essentially it says that we will have this uniform distribution with respect to some measure if every time we integrate against this sequence of probability measures, and the limit will converge to this integral over the limit measure. And here observe that, I will put it here so that you can see, the integral of f with respect to this one is by definition simply taking the average over the set of points. So it's 1 over xn, sum x in xn, and then you evaluate f at x, because this is the integral against the delta x. So it's really taking these finite averages and then trying to show that it converges to this integral, whatever the limit measure is. Okay. So that's a very general definition. I lost the eraser. Yes? Oh, looks like a mouse. I see. I see. Thank you. Okay. And before going back to elliptic curves, let me give you a couple of examples which already, I think, illustrate kind of the relevance of these definitions. Let me also say that, no, just leave it like this. Examples. So I guess the simplest example is something that we learn in algebra, I guess, when we learn about roots of unity, complex roots of unity. Let's say if the space, the ambient space is S1, so this is just the unit circle, I will see this as complex numbers of norm 1. And then as an example, you can take xn to be the collection of roots of unity of order n. So this is what? How can I describe this? Easily just saying that these are the complex numbers which are n roots of 1. And we know that if we draw these points, it will depend on n. But let's say if n is 4, you will have 4 points, 1, I, minus 1, minus I. But if I do n equals 100, then I will have 100 points equally spaced around the unit circle. And this should become uniformly distributed in the limit to the natural measure on the unit circle, which is the arc element, the Lebesgue measure normalized by the length. So in this case, we can say that these sets of points are uniformly distributed with respect to the measure, the Lebesgue measure, which is like, Lebesgue measure, normalized Lebesgue measure on S1. And in coordinates, you can write it as d theta divided by 2 pi, where theta is the angle. And this formalism is just saying that if you take a test function, a continuous function on the unit circle, and then you take the average over the roots of unity, and then you make n go to infinity, it will converge to the integral of f along the unit circle with respect to this measure. Okay, this is not surprising, just because in the picture we already see that all these points are uniformly, they are equally spaced. What is less trivial, I will say, is that the same happens when instead of taking all roots of unity, we only take the primitive ones. So when xn, let's say prime, is primitive roots of unity. So z is a complex number, but now z is a primitive nth root of unity. For example, in this picture, if you look only at the primitive roots of unity of order 4, you only get I and minus I, right? So you have less points. And in general, they're not so nicely distributed that it looks like, but in the limit, one can show that actually these ones are also uniformly distributed with respect to the same limit measure. Okay. Since this really it's presented in terms of measure theory, it's not surprising that many of the results about uniform distribution actually come from ergodic theory and dynamical systems. But in many cases, when one deals with objects that come from number theory, usually the techniques, the general methods coming from ergodic theory do not apply, because somehow ergodic theory is always about the generic cases, and number theory is very like special cases instead of that. Okay. If you have questions or comments, just, yeah, David?
Yeah, so in this example, when you have two different n's, of course you find a big enough n that kind of contains both of the previous n's, right?
For the first example.
In the first example,
yes.
Yeah. So don't you need some conditions like this for the or is it like can it be totally arbitrary?
Can be totally arbitrary. They can be all of them disjoint. They might not have any intersection. Sorry?
For the case that you were looking at for Hecke, what was it? Orbit?
Yeah, Hecke orbits, yes.
Is it like more like this example, or is it?
Yeah, I think it depends on the n. If you restrict to some n's, to some subsequence of Hecke orbits, again, you can assume that all of them are actually disjoint. They don't intersect.
Okay.
Yeah. Yes. Okay. Maybe give you one more example. Okay, sure. Second example. So this is 1, 2. And this actually really comes from, the proof that I know really comes from dynamical systems. But it's also related to the Diophantine approximation, which is now we take X, will be essentially the same space, but in a different presentation. Just R mod Z. And now we take a number alpha, which is real, but it's not rational. Then we can take Xn to be the multiples of this irrational number in this quotient. So we take K alpha, let's say, well, K alpha. I should put a bar or something, I guess, bar in the quotient. So this is the reduction mod 1 of this number with k from 1 to n. So we take the first n multiples of this irrational number and we take the reduction mod 1. So that gives us different points in here. And then here again there is uniform distribution. And this is only happens, of course, if alpha is irrational, because if alpha is rational, then this becomes a finite set. So there is no hope that you will get uniform distribution over the whole space. So we see a dichotomy here between rational and irrational multiples. So again, is uniform distribution with respect to, in this notation, is just, let's say, dx. But it's the same measure if it's just two realization of the same space. And yes, okay. Okay. And now let's connect this general setting, this general uniform distribution problems with these Hecke points in the case where the base field is the complex numbers, okay. So this section 4, it's about equidistribution of Hecke orbits over the complex. So now our base field is fixed, it's the complex numbers, hence we have a lot of theory that we can use. Here the reference, where actually this result is proven, is a paper by Clossel and Ulmo, 2004. The title is just equidistribution of Hecke points. So if you just Google equidistribution Hecke, Clossel and Ulmo, you will find this paper. Okay, so what is it that we do here? We will use the uniformization of elliptic curves over the complex. So what we do here is that this abstract space can be identified with the set of all possible tori over the complex. So this is the fact that every elliptic curve can be realized, if you look at the complex points, can be realized as a quotient of C mod lambda. This already appeared yesterday. So where this guy is a lattice in the complex plane, and this is an isomorphism of, let's say, complex Lie groups. So over the complex, this category is the same one as this one. And then there is this nice uniformization by the upper half plane if we defined H as all the elements which have positive imaginary part. This already appeared before. Then we know that there is the group, let's say, GL2 plus R is acting here by Möbius transformations. So A, B, C, D tau is A tau plus B, C tau plus D. And then the discrete subgroup gamma, which is SL2 set. This acts in a nice way over H, is such that the quotient space gamma mod H mod gamma, sorry, is actually gives all is in correspondence with all the complex tori. Just send in some class here of tau. You send it to the torus C mod set plus tau set. Everything that I'm saying here is quite classical. You will find it in several books, in particular in the Silverman's book, when studying elliptic curves over the complex. Okay, and all of this that I'm saying is just to present you a natural measure on the moduli space of elliptic curves over the complex, which actually comes from this hyperbolic space. So on the upper half plane, we have the measure d mu equals dx dy over y squared. This is the natural hyperbolic measure. Hyperbolic measure is the natural one because it's the one that is invariant under the group that is acting here. And this one has measure, gives total measure pi over 3. So we have to normalize it to get probability measure. So you just divide by this constant. So I will call mu 0 will be 3 over pi times d mu. And now we have a natural probability measure on this quotient, hence on the space of all tori. hence on the space of all elliptic curves over C. Of course, trying to translate this measure to this space is quite, we have no idea how to describe it, I guess, here. It's very complicated. But identifying all these spaces, we can just use this natural probability measure. And this will play the role of the limit measure in this problem of equidistribution of Heike orbits. Let's see. Okay. So now we have a natural measure on our ambient space. And let me also translate Heike orbits that were defined here. Let me translate them into this setting. So the Heike operator becomes the following. So Tn und tau, so tau, or the class of tau, is an element on this quotient. So what you get if you just use all this complex uniformization theory, what we get is that this operator, the image of this point will be, of course, again a divisor. Now it will be a divisor on H mod gamma, and this will be just gamma acting on tau, the class of that, where gamma runs over all possible matrices, 2 by 2 matrices with integer coefficients and determinant n mod the action of SL2. SL2 acts here just by multiplication, so M2n set is by definition all matrices 2 by 2 matrices, integer coefficients, determinant n. And actually this gives another approach to the computation of the degree of this divisor, just by showing that if you look at these matrices and you look at the action of SL2, then the quotient of that has exactly sigma 1n points. So the degree of this one is sigma 1n, where sigma 1n was the sum of divisors of n. Okay, so now we have translated Heike orbits to this setting, and we have a natural measure on the ambient space, and now I can present the theorem of Claussel and Ulmo, which by now should not be surprising, is what we expect. So Claussel and Ulmo, 2004. So what's happened is that, let's say, for all points in this quotient H mod gamma, if I look again, I will construct this probability measure associated to this divisor. As before, will be just an average, so it will be 1 over sigma 1n, the degree of this divisor, and then the sum of deltas at each point, let's say gamma tau, where gamma runs in this set. So this is just this translation of this divisor to the corresponding probability measure. And what's happening is that this will converge weakly as n goes to infinity to this normalized hyperbolic measure. So d mu 0 being 3 over pi dx dy over y squared. This is a weak convergence of measures. So this is the statement of the first equidistribution result about Heike orbits. We know in this case that this measure, it's supported everywhere on this space. Hence, as a consequence, we get that actually Hecke orbits are dense. And at the end of this lecture, I will mention some applications of these results. Let me see the time. Yeah, okay. What I want to do now and for the rest of the lecture is actually give you an idea of the proof, because I think it involves a lot of nice tools. And then later I will mention that this approach that is used here actually doesn't work if you want to change the base field. So instead of doing this over the complex, you want to do it over the p-adic numbers, then it's not going to work, because basically we don't have this nice uniformization theory for all elliptic curves over CP. So this is a very special setting where you can use complex uniformization and all this machinery. Okay, so as I said, for the rest of the lecture, I want to give a sketch of proof just to show you the techniques and tools that are used. Okay, and you will see how special this is. It's really difficult to kind of use the same techniques in other settings which are different from these ones. Okay, so what we are going to do, so just by definition, given a function which is bounded and continuous, we want to prove that the integral of f with respect to this measure converges to the integral of f with respect to this normalized hyperbolic measure. So f, it's what is called a test function for this equidistribution statement. It's in the set of all bounded functions on this space. So this is the set of all bounded and continuous functions on H mod gamma. And might look weird at first, but instead of working on this space, we are actually going to work in a larger space. So the set of all bounded and continuous functions is contained in the L2 space of all functions on this quotient, which are the L2 space with respect to the normalized hyperbolic measure. And this is a much larger space, but it has a richer structure. So this is a Hilbert space with the natural inner product f g equals the integral of f tau g tau bar with respect to the hyperbolic measure over the quotient space. And then we can use tools from spectral theory on this space to actually get the equidistribution. So we go to this larger space, and then we also think of Tn actually as operators on this L2 space in a natural way. So we can define, let me do it here. We can also define the same Tn, but now will be an operator from L2. I will just write L2 is L2 from this space. I will just call it L2 all the time. This is the operator defined by Tn of f in tau will be just the sum of f gamma tau. So it's the average over the divisor. Sorry, not the average. It's the sum over the divisor, where the gamma is as before. So it's in gamma as m2 set determinant n mod gamma. And this, I mean, this is I didn't explain this in the first lecture, but this is deeply related to the theory of Hecke operators on modular forms. This is like the weight zero version of that, also with a different normalization of the operator, but this is the one that I will use now. And here we see that we want to show that for all points in the space, if I look at T and F and I evaluate at tau and I divide by the degree, I want to show that this converges to a constant, a number that is independent of tau, and this is just the integral as n goes to infinity. So this is what we want to prove. This looks like it's a pointwise convergence. So for every tau, you want to prove that this quantity goes to this constant. Instead of that, it's not difficult to be convinced of the fact that this is related to the problem of proving convergence in L2, which is a different notion, but is related. So by standard arguments, actually approximation arguments, it is enough to prove actually that if I look at this difference of this against the integral 1 over sigma 1n t n f as a function, as an element in L2 minus the constant given by the integral, this goes to 0 in L2 norm as n goes to infinity. Okay, there's a standard way of connecting these two problems. Can be a bit technical, but I will just skip that part. So now we are really translated everything into a problem about operators in L2, and then the convergence here now means convergence in L2 norm associated to this inner product here. Okay, and as I said before, we are going to use a spectral theory. In order to do a spectral theory, we need an operator on L2. So on this space L2, we have the hyperbolic Laplace operator. I will just call it delta, is minus y square dx square plus dy square. So this is just the hyperbolic version of the usual Laplace operator in dimension 2, in real dimension 2. Sorry, I should have said this, but every time I'm writing the tau as x plus iy, so every time I write x and y, I mean real part and imaginary part. And this operator is a differential operator that can be defined on L2 by standard extension arguments, because this in principle is only defined on, let's say, smooth functions. But smooth functions here are dense, so you can extend it to some operator here. So we have this operator and a spectral decomposition theorem. So what is that? So we learned, let's say in linear algebra, that when you have a nice operator on, let's say, a vector space, in this case a Hilbert space, you want to essentially diagonalize your operator in spaces of infinite dimension. This becomes more subtle, but still in some cases you can do it. And this is one of the cases where you can do it, because this operator is, has very nice properties. It's a non-negative operator. It's a self-adjoint operator. And then we have the following theorem. We have that the space L2, it's a sum. There's a part which is a discrete part. It's an infinite sum of eigenfunctions from k equals 0 to infinity. And there is another part which corresponds to a continuous spectrum, which is Of course, I will define it right now. So this collection of elements is a orthonormal system or collection of vectors which are eigenfunctions. So delta phi k, it's lambda k phi k. And these eigen values, they form an increasing sequence, an increasing sequence of positive or non-zero numbers, because this operator is non-negative. So this is like 0 is this first eigenvalue that corresponds to the function constant equal to 1. And then you have positive numbers. And then actually this sequence goes to infinity. And these are actually called mass forms. These are non-holomorphic automorphic functions. They are completely invariant under the group because we are working with functions which are defined on H mod gamma, which is the same thing as working with functions on H, which are gamma invariant. So these are like weight 0 modular forms, but they are non-holomorphic, with the only exception of one. This is the only holomorphic example. All the other ones are non-holomorphic, and they were introduced and studied by Maas, which was a student of Hecke. And all of this is part of what is called the spectral theory of automorphic forms and automorphic functions. And I will also give a reference for this in a moment. Let me just finish this statement. So we have a discrete spectrum correspond to this discrete collection of eigenvalues. And then this other space kind of corresponds to Einstein series. So this is a space which is isomorphic to L2 R plus. So this is the usual L2 space with the Lebesgue measure. And this space isomorphic to this L2 space via the Einstein transform. So we would like to have here Einstein series, but actually Einstein series are not L2. But we can use Einstein series to define this map as follows. So there is a map E that goes from L to R plus. I will just realize this isomorphism. And this is just sending an element here, H. Will define then an element in L2 of H mod gamma. So I have to define it like here, like this. So this will be an element in L2 of gamma mod H. And this will be given by an integral transform, integral from 0 to infinity, H of t, E tau 1/2 plus IT dt. And this is where the non-holomorphic Einstein series appears, which is kind of similar to the one that we saw this morning, but this is, in some sense, is it's a much more simple object. This is a weight 0 non-holomorphic Einstein series. Is defined, can be defined as follows: so it's 1/2 sum over all m and n integers, which are coprime. 1/m set plus n to the 2s. So it's really similar, but much it's definitely more simple than the one that we saw this morning. So tau and h and s. In principle, this is a complex number that has real part larger than 1 for this series to converge absolutely. But one can prove that this object has meromorphic continuation to the whole complex plane. So this is meaningful, and actually there will be no problem in that line. So with meromorphic continuation to S in the complex plane. So as I said before, in this L2 space, there are no really Einstein series, but the Einstein series can be used to construct this map. Okay, so the idea of this proof of the equidistribution of Hecke orbits over the complex is to exploit this spectral theorem decomposition, because instead of working with a general test function, NEF, which is, let's say, bounded and continuous, you can actually decompose F as a sum of multiples of these guys and some element coming from L to R, and then try to prove equidistribution piece by piece, essentially.
Is it from R plus to C or R plus to R?
I think you can take everything C. I guess I put C here. Yes, should be C. Yes. Yeah, you can put everything with complex values. Yes. That's better. Okay. So now, okay, I really have to. So now, since we started with a function which is bounded and continuous, and this, of course, is contained in L2, we can do the spectral decomposition of one particular element. And actually, when this function is bounded and continuous, the spectral decomposition is like it's converges nicely to the F. So this will have, I will just split the first term here. I just said it, but now I'll write it. So the first eigenvalue, I said it was 0. This is because this eigenvalue corresponds to the function, what should this be? Constant, the constant function. Just 1, right? Because I already normalized the measure, so it should be 1, constant 1. Okay, because this is an orthonormal system, so I have to make sure that all the elements have norm 1 as well, so that this formula is correct. I don't have to normalize here these vectors. Okay, so I will have the first contribution corresponding to the function 1, and then I will have the rest of the discrete spectrum contribution. So this will be F against Vk, K going from 1 to infinity. And here I will just say that this other part is just some E of some H with H in L2 R plus. I don't have to be precise about which H it is, but it comes from some H. So the first term in this decomposition is by definition the integral, because this inner product gives me really the integral of F against 1. So this is really the integral of F over the whole space with respect to the normalized hyperbolic measure. Hence, if I put this on the left-hand side, I just want to show that F minus this thing now, let me do it like this. If I do F minus, then I will just have this contribution. So what I want to show now is that, what do I want to say? I want to say that, okay, I just want to say that, okay, just leave it like this. So I recognize that the first contribution in this spectral decomposition is exactly the integral. That should be the limit in this L2 convergence. And what I want to do now is actually apply these Hecke operators. So I forgot to say it, but there's this important remark, is that we can assume in this spectral theorem that these functions, these phi k, they are all eigenfunctions of these Heike operators. So Tn phi k equals a k n. So there is some complex number times phi k. And this is easy to prove. This is because the Tn's are Hermitian. Operators, and also because they commute with the Laplace operator. With the hyperbolic Laplace operator. So diagonalizing Tn and diagonalizing delta, you can make what's it called, simultaneous diagonalization. So that means that even though these are at first only assumed to be eigenvalues of the Laplace operator, you can further assume that they are actually also eigenvectors of these Heike operators. Yeah.
Can you explain again why I0 is constant?
It's just because this corresponds to eigenvalue 0, and this is a differential operator, and this is one of the possible eigenfunctions that you have, right?
This eigenvalue is 0 because?
I'm collecting all possible eigenvectors of my operator, delta. One of them is the constant function. The constant function, if you do delta 1 of the constant function, this is by definition delta x plus delta y, blah, blah, blah. So this, of course, is 0. You take a derivative of a constant function. So this one has to be one of these eigenfunctions, and I'm just putting them in the first place. And all the other ones, I will just say these are the other eigenvectors. And one can show that actually 1 is the only one. Only constant functions can have eigenvalue 0.
All right.
There are no other vectors which have vanishing, which satisfy this differential equation. Okay. This is again because harmonicity properties, properties of harmonic functions. Yeah. Yeah. Thank you. Okay. Okay, so now that we can assume that all the vectors here are eigenfunctions of the Heike operators. Again, this is very standard. It's the same thing that we do when we work with holomorphic modular forms, and then we construct bases of eigenfunctions. What's going to happen is that in this equation, if we apply Tn, so I will apply Tn here on both sides, I will get here Tn of f. And here I have a constant, and it's clear that, let me do 1 over sigma 1 n here, so that I normalize this operator. So the constant goes to constants. So this, again, this integral doesn't change. It's the same value. It's the same number. And now if I apply Heike operators here, I get the eigenvalues. Divided by sigma 1n, and then phi k. So this is the eigenvalue that I got from this hypothesis, and then just the normalization. And then this is the sum from k1 to infinity. And then I get, I have 1 over sigma 1 and Tn acting on this Einstein transform. OK, this is what I get. So the goal is to prove that this one, this term, converges to this integral as n goes to infinity. That's what we want to prove, which is equivalent to say that this part goes to 0. So this is what we want. This goes to 0 as n goes to infinity. And for this, what we need to show, it is enough to show that each term in this infinite sum goes to infinity, because it's easy to control these quantities which are here, and it's easy to control this infinite sum. So it's not difficult to see that it is enough to prove that this quantity akn, the eigenvalue divided by sigma 1n goes to 0 as n goes to infinity, and I have to do the same thing, but now for this part of the Einstein transform. So 1 over sigma 1n Tn EH, at least in L2 norm, goes to 0. Because at the end we said that we just want to prove L2 convergence. Okay. And then here is we see that we need some kind of non-trivial results about the eigenvalues of the Hecke operators acting on mass forms, on non-automorphic automorphic functions. And for this we need non-trivial bounds for these eigenvalues. So we have the following bound. So akn grows at most as constant, let's say, times n to the 1/2 plus 7 over 64. I have to put, what do I have to put here? Let me state this correctly. Let me actually be more precise. The precise bound is actually with sigma 0n times n to the 1/2 plus 764, where sigma 0 is now the sum of the number of the number of divisors of n. So it's sum of 1s for every divisor. So number of divisors of n. Okay, and this is a non-trivial bound. I'm just using here a bound obtained by Kim and Sarnak, a famous bound, 2003. And then with this, it's easy to see that if I divide by sigma 1n, then this quotient will go to 0 because sigma 1 is at least n. So this exponent is less than 1. This number is easy to prove. This is exercise in, let's say, analytic number theory, that this is at most a constant. It's like n to the epsilon. It really grows slowly. So this is like this for any epsilon. So for any epsilon, the number of divisors of n grows slower than n to the epsilon. So what we get is that this quantity akn over sigma 1n, putting everything together, you just compare the exponents, goes to 0. But here's where you need this non-trivial bound for the eigenvalues of Hecke operators, which is a very important problem in general. Yeah?
How much more trivial is that inequality? Is this complicated to prove?
Yes, it's complicated. It uses L2 estimates on L2 special values of L2 functions in some, I forgot, symmetric products. I don't know, the things that I really don't understand. For me, this is a black box.
Okay, there's a connection with the Ramanujan
Yeah,
inequality?
definitely. So the conjecture is that the Ramanujan Peterson, how do I write this? Peterson conjecture, which is open for non-automorphic forms, is that actually akn should be, what should be? 1/2, right? Should be sigma 0n and 1/2. So that's why this is written like 1/2 plus something. This is how far it is from the conjecture. And I think the trivial bound is when the exponent is 1. That's the trivial bound. But the trivial bound, when you get a 1 here, is not good enough to get this limit. It's exactly like the boundary. You need whatever that is less than 1, whatever that is better than the trivial bound. But you don't need the full conjecture. That is way too much. So this is the analog of this the Linnaeus bound, but in the non-homomorphic setting. And time is okay. I just want to say that this is the easy part, because this comes from Einstein series, and using the definition of this Einstein transform, it's easy to show. Using that, let me just write it. Using that, you can act with the Hecke operator on the Einstein series directly. You get that Tn E set S. This is the non-homomorphic Einstein series that we used to define the Einstein transform. It has an eigenvalue. This is always the case. Is n to the s sigma 1 minus 2s n e set s. So the Einstein series is also an eigenfunction. Then you can use this to control this contribution and show that this goes to 0. As usual, again, there's another sum of divisors. In general, sigma a n is the sum of d to the a, d divided n. So using that, we get this missing part, so star. But this is the easy part. You don't need to use any fancy bound. It's really just put in what is the right s here. The s was 1/2 plus it, and just comparing this with sigma 1n and so on. Okay, so that's the end of the proof. As I said, I just wanted to show you what kind of tools are used. So it's really nice to see that one has to use this kind of spectral theory techniques. And also we see that there's this non-trivial bound for the Hecke eigenvalues on non-homomorphic modular functions. And yeah, we are using a lot of tools from different areas, let's say. And then I guess I will have to do it the next time, but I wanted to explain how this uniform distribution result for Hecke orbits over the complex can be used to treat one of the cases when one studies the uniform distribution properties of CM points. And then this has application to some arithmetic properties of singular moduli. This I will come back to this in the next lecture. Thank you.
So, questions for Sebastian? Yeah.
I am not. I did not understood why applying Tn
Yep, to this.
over sigma 1n in the first term actually remains constant, because we just defined ak of n in that equality.
Yeah, this I needed only for these ones.
Right?
For this one, yes. But if you remember the definition of T and F, this is a new function that evaluated at tau gives you the sum of the same function evaluated at gamma tau, right? So you're moving the tau with some elements, with some matrices, the action of some matrices of determinant n, 2 by 2 matrices, up to the action of gamma. So if f is a constant equal to 1, you just get a sum of 1s. How many times? Exactly the degree of this divisor, but we are normalizing the operator. So you will get a sum of 1s that will add up to sigma 1n, but sigma 1n you are dividing with. So what if this is a constant, c, this will give you sigma 1n times c, where sigma 1n is just the number of terms in this sum. That's why this operator sends constants to constants.
Perfect.
Yeah.
Thank you.
Yep.
More questions? Yes.
So this bound, they only really need that it's better than the trivial bound, right?
Yes, only need better than trivial
Maybe
bound.
there's an easier argument to
Oh, I don't remember exactly how's the development of these bounds. I think now there's even a better bound by now. It's 5 over something, I forgot, 28, I think. But yeah, I mean, at the time where this first proof was presented, this by Closel and Ulmo, they were using this one. But it is true. It's important to notice that you need whatever, which is of the form sigma 0n, let's say n to the something less than 1. Okay. Yeah. So better than trivial.
Yeah, I think he's asking what's the first non-trivial bound. I mean, is there something simpler than Kim-Sarnan that does the job?
Yes, historically, I don't remember what comes before them. I really don't remember. I will try to find out about it. Probably in their paper, probably they mentioned what were the first bounds that people obtained. I will try to find it.
Yeah, please.
Is this studied for other modular groups like gamma 0n or something?
Yes, this can be done with. One has to be a little bit careful with, well, also even with the definition of Hecke operators, you have to take into account the level structure. But I think, yes, this should be quite, yeah, the method is quite general for the complex setting. So in the complex setting, this is quite doable, yeah. Yeah.
Well, if there are no further questions, we thank
Thank
Sebastian
you.
again, and we start the
¿2004? Sí, 2000, un año después.
¿Estaban como esperando esta cuota o no?
Puede ser, no sé, es que me acuerdo que la primera vez que Ricardo